Fresh pie. Save me a slice. That's good. That's good. It's enough slices. Hey, it's e to the I Pi week here at Polymathematic HQ. I was probably super loud. Hey, I'm going to be taking a look throughout the week at what has been called the most beautiful formula in mathematics. Most beautiful identity that there is. Euler's identity, e to the I Pi plus 1 equals 0. Now, this video and the next are really kind of throat-clearing videos. It is the last video of the week. I don't know when it will go up, probably Thursday, where I'm going to get into actually trying to understand what on earth this identity means. But in that video, I'm going to refer to proving two different topics. The first thing I wanted to focus on is, what is this number e? If we can at least say something useful about e, then maybe we can figure out what on earth an identity like this could mean. And you can define e a lot of different ways, and in fact it was discovered independently several different times throughout the 17th and 18th centuries. But the method that I'm going to look at here is to define e as the limit as some number approaches infinity of 1 plus the reciprocal of that number raised to that number's power. So for example, if n equals 2, what we're saying we want is 1 plus 1 over 2, 1/2, and then that sum raised to the second power. If we want to let n equal something like 6 instead, we would have 1 plus 1/6, that sum raised to the 6th power. As we let this number n get larger and larger, we can see that that quantity is getting closer and closer to 2.7, 1828, 1828, 4, 5, 9, 0, and so on. That is the number that we call e, or sometimes we call it Euler's constant. Again, it has different names because different people discovered it over time. There are even more general things we can do with this definition. For example, it doesn't just have to be 1 plus the reciprocal of the number that we're letting grow toward infinity. It could be 1 plus 2 over n, and that would end up giving us e to the second. It could be 1 plus 3 over n, which would end up giving us e to the third. So in fact, in general, whatever number is above n is the power of e that we're interested in. But for now, we're just going to stick with regular old e to the first power, and we are going to prove this limit as n grows to infinity. What is the limit of 1 plus 1 over n to the n power? So the first thing to notice about this limit is it's kind of existing on multiple levels, and we tend not to like that when we're trying to solve equations or compute limits or do anything like that. You can see we've got the variable in the exponent itself, but then we've also got the variable kind of in the main level of the equation. It's hard to deal with this, and so we need something that's going to take the exponent and bring it down to the main level. The thing that does that is the natural logarithm. So we're actually going to assume this limit is some number, and we're going to take the natural log of that number. Now, at this point, you might think that we're kind of getting ahead of ourselves. If you know that the natural logarithm is the inverse of the exponential function, you might think that we're kind of going out of order here. Historically speaking, though, the natural logarithm actually was developed earlier than the exponential function. It preceded e. Now, I am going to do something a little bit ahistorical toward the end of this to kind of undo this natural log step, but historically speaking, this part is okay. This is going to be the same thing as the limit as n goes to infinity of the natural log of 1 plus 1 over n raised to the n power. And again, the whole idea behind why we did that was that when you take the natural logarithm of something, what was an exponent becomes a multiplier. And so in fact, we can now say this is the same thing as the limit of n growing to infinity of n times natural log 1 plus 1 over n. Now, it's worth asking right now, why are we even going to all of this trouble? Can't we just plug in infinity into the actual expression and see what it equals? The answer is no, we can't. Again, go back to this picture. What's happening here as we increase n is that on the inside of the parentheses, that 1 over n part is going to get smaller and smaller. So the inside of what we're raising to the n power is going to get closer and closer to 1. 1 plus a smaller and smaller number essentially becomes indistinguishable from 1 plus 0, which is 1. The reason that matters is 1 raised to any power just stays 1. So that might make us think that the limit of this expression is going to be 1. Obviously, when we use modern computation, we can see that's not the case. We're going to get a much larger number than 1. So it must be that even though it's getting really, really close to 1, because we're also raising it to an infinitely large power, remember n is also up there as our exponent, that large as you want exponent is basically going to counteract the small as you want 1 over n part and mean that this grows towards something else. When we're back over here, having used the logarithm, we can start to get a sense of what we mean by that something else, that small thing being raised to a big power, and how those are balancing out. If you plugged in infinity right now for n, this limit would evaluate to infinity, that's the n part, times the natural logarithm of 1 plus 1 over infinity, essentially. Now, 1 over infinity doesn't really mean anything as far as numbers are concerned, but 1 over an infinitely large quantity is essentially indistinguishable from 0. And so really, this is going to evaluate to something like infinity times the natural log of 1 plus 0, and the reason that matters is 1 plus 0 is 1, and the natural logarithm of 1 is 0. So in fact, when we attempt direct substitution, we end up with what's called an indeterminate form, infinity times 0. There are several such indeterminate forms to watch out for when we're taking limits. Infinity times 0 or 0 times infinity, infinity over infinity, or 0 over 0. When we get these forms, we can't quite say what this is supposed to be equal to. It's tempting sometimes to say, well, I guess it must be equal to 1, but the fact is infinities can grow at different rates, and what matters for the purpose of the limit is the rate at which the infinities are growing. The same thing is true as things get closer and closer to 0. They can get closer to 0 at faster or slower rates. So we have to use a tool whenever we see indeterminate forms of this kind, and that tool is called L'Hopital's rule. What L'Hopital's rule tells us is that if we have some limit as x goes to 0 or infinity or really any particular number of f of x over g of x, that is if we can state it as a quotient of two functions, and this leads to an indeterminate form like 0 over 0 or infinity over infinity, then provided f of x and g of x are well behaved in some sense, I'm not going to get into that in this particular video, but it's things like g of x can't be 0, they can't be switching signs infinitely many times, stuff like that. Provided that they're well behaved, we can say that this limit is going to be the same thing as x approaches whatever particular value of the quotient of their derivatives, f prime of x over g prime of x. Again, you might think, isn't this ahistorical? Surely this developed much later than when we started to figure out the value of e, and the answer is no. Actually, one of the guys who originally computed e, a guy named Jacob Bernoulli, this rule, although we call it L'Hopital's rule, he actually developed. We could just as easily call it, and some people do, Bernoulli's rule. L'Hopital's rule, or Bernoulli's rule, or whatever we want to call it, requires that we write the original thing we're trying to take a limit of as the quotient between two functions. So we need to be able to take this n times log of 1 plus 1 over n portion and turn it into a quotient. What that's going to look like is the limit as n grows to infinity of that natural log portion, natural log 1 plus 1 over n, and then I'm going to take this n times, and I'm basically going to turn it into division by its reciprocal. So that is the denominator itself is going to be 1 over n. This is now in a format where you'll notice if we plug the infinity in, so to speak, we get this part going to 0, natural log of 1, which of course is 0, and again, as n gets infinitely large, 1 over n would also be 0, so now we've met our requirements. We have an indeterminate form, 0 over 0. We are ready to apply L'Hopital's rule. So we're going to take the derivative with respect to n on both top and bottom of this fraction. One thing we'll need to note is that because the inside of the natural logarithm here isn't just n or x, it is itself a function, we'll have to use the chain rule when we take our derivative. But this should be the same thing as the limit as n goes to infinity. For our denominator, the derivative of 1 over n, we can simply apply the power rule because, of course, this is the same thing as n to the negative 1. So that becomes negative 1 n to the negative second, or what we more typically write as negative 1 over n to the second. For the numerator portion, derivative with respect to n of natural log 1 plus 1 over n. Again, we need the derivative, first of all, of the natural log function, which is the reciprocal function, 1 over 1 plus 1 over n. But then we need to multiply it by the derivative of this inside portion because of the chain rule. The 1, when we take the derivative, just goes to 0, and 1 over n, we actually just said what the derivative was, negative 1 over n squared. We're going to take this, put this on top of our fraction, and you can tell that what happens when we do this is that the negative 1 over n squared portion cancels out. And so that's going to leave us, after we erase some of this other work, with the limit as n grows toward infinity of simply 1 over 1 plus 1 over n. That is just this portion here that did not cancel out from the chain rule thing we did a second ago. This can now be evaluated directly because, of course, as we plug in infinity here, as the denominator of that fraction gets infinitely large, that portion goes to 0, and so this ends up being 1 over 1, which is 1. Now, it would be nice to say we're done. We showed that the limit is 1. But remember, we used a little trick at the beginning of this process. Way back here, to be allowed to move that exponent of n down to the main level of the equation, we took the natural log of the original limit. Presuming that's a number, that's not all that ahistorical. But to now undo that process, we might think, well, let's use the inverse of the natural log. And this is where we get into a little bit of trouble in two ways. First of all, the natural log wasn't really thought of a function right after its development so much as just another number associated with whatever the original number is you were taking the natural log of. And so it's a little weird to kind of undo that process the way that we say undo a square by taking a square root. The second problem is the much bigger problem, though. We know now that the exponential function is the inverse of the natural log function. But the whole thing we're trying to do here is show the connection between this limit and e, the base of the exponential function. So it feels a little tautological, a little circular logic kind of thing to say, oh, now let's go ahead and raise all of this from a base of e, and then we can say, oh yeah, our answer is simply e to the first power. That's true, but again, that's kind of setting the cart in front of the horse, mathematically speaking. So I'm going to do something that might seem a little bit strange, and again, is definitely ahistorical, but at least I'm not putting the cart in front of the horse. I'm going to imagine now that we can take the inverse of the natural log of 1 without respect to thinking about what this is actually equal to. And there is a way to define this without worrying about the exponential function at all. The natural logarithm function was developed originally in part to be able to say something interesting about a rectangular hyperbola, what today we would simply call the reciprocal function, x times y equals 1, or in functional notation, f of x equals 1 over x. The natural logarithm is specifically what we get when we look at this point 1, 1, and then beginning from there, we think about the area under the reciprocal curve. If this is some point x further along down the number line, in modern notation we would put it this way: the natural log of x is equal to the integral from 1 to x of 1 over t dt. The integral part is talking about the area under this curve. The curve itself is the reciprocal function, which I'm representing here using the variable t. And again, we want to begin that area process at 1 and then move forward for some x further down the number line. The connection here is that when we talk about undoing the natural logarithm of 1, what we actually mean is, what is the specific future point that would guarantee this area in here is equal to 1? How far away from x equals 1 do we have to move to get an area under that curve of 1? And the answer to that question is e. That is, if you look at the area under the reciprocal curve from 1 to e, you will see that that area is 1. And so it is in that sense that we can say, hey, the inverse natural logarithm of 1, the number that we would plug in to the natural logarithm function to get back 1 as a result, that is what we call e. You could verify by actually drawing a bunch of little rectangles and computing their area that it's a number that gets really close to 2.71828182845, I don't know, a lot of other digits. Again, is this a little ahistorical? Am I doing it a little out of order? Absolutely. These are not the tools that, for example, Euler put together to prove that E is E. Euler did a whole different thing by using the polynomial expansion of 1 plus 1 over n as you let it expand to higher and higher powers, squaring it, cubing it, etc. But for our purposes, it is enough to show, using L'Hopital's rule or Bernoulli's rule, whoever you want to name it after, that we can compute this limit and the limit definitely is equal to e to the first power. So I hope that's been helpful for you. Again, I'm really excited about the videos I'm putting out this week. Watch this space tomorrow. Subscribe if you're not already subscribed, as I'll be posting another video analyzing this particular picture, trying to prove a certain limit about the tangent of a very special angle. And again, all of that is going back to the most beautiful formula in mathematics, e to the I pi plus 1 equals 0. We are justifying and then trying to develop an intuition for what on earth such a formula might mean. Thank you for watching. Like this video if you've liked it, subscribe if you're not subscribed, and I will see y'all next time.